In this video, we'll discuss ancient Chinese mathematics. Now, unfortunately, we don't have the records like we do for other civilizations about the ancient Chinese. Part of that is because much of their work was done on bamboo with ink, and the bamboo has disintegrated over time. Additionally, there's different times in history when the emperors have had book burnings, such as the 213 BCE, which then limits how far back our history goes into knowing what was known at what time period. However, we know that the ancient Chinese were thriving during much of the time that Europe was in the Dark Ages, and before that as well. And much of what we think about as coming from the Europeans during the Renaissance period was well known and actually determined often by the Chinese in prior texts. Now, when we look at what did the ancient Chinese know, there are many different concepts that are important to recognize. They knew about numeral systems and decimal fractions. They could work with negative numbers, something that the Greeks really struggled with. And they even enhanced the values of pi. They were able to solve equations using Horner's method, and they created the Pascal triangle hundreds of years before Pascal even considers it. They utilized the binomial theorem, something that's tied to the Pascal triangle. And they were able to solve linear algebra forms with matrices and systems of equations. They could solve equations with double false position, and they even constructed a form of descriptive geometry. So there's a lot of mathematics that came from the ancient Chinese that did travel through many of the roads that led to trade and then were brought into Europe as well. Now, there are different books that we do have some of the texts from that have been saved in things like tombs, such as the writings on reckoning. This is a text that comes from about 200 BCE, and there's somewhere between 180 and 200 bamboo strips, often cited to be about 190 strips now that were written in ink on them. And it had 69 problems on it, covering a wide array of topics from concepts in arithmetic and reasoning and proportion and different types of geometry, as well as financial type problems. And what's unique about it is not only do they include the problem, they include the answer, and they include a method for how to solve them. Now let's look at a problem from the Writings and Reckoning, here on strip 30 and 31. Now there are 3/7 Zhu of gold. How much would one increase to make it 7/9? It gives an answer. Increase it by 22/3 Zhu. Then it even gives a method. It says the denominators are multiplied together to make the divisor. In other words, we're going to multiply and make a common denominator of 63. Next, it says the numerators multiply the denominators reciprocally, making each a dividend of its own. In other words, we're changing these to equivalent fractions. So that would have become 27/63 and 49/63. And then it says reduce the greater by the lesser, then the remainder is the increase. In other words, subtract 27/63 from 49/63, and the solution to this problem is 22/63 Zhu. Now, the work from the writings on the reckonings led to the 9 chapters of the mathematical art. We don't know an exact date as to when this document was constructed, but we do know that a commentator was created around 263 CE. So there's about a 400-year time period that likely was the construction of the 9 chapters, as well as additions and modifications to it. And it's called the 9 chapters because there's literally 9 chapters to this text of 246 problems. And again, it's yet another text coming from the ancient Chinese showing a wide range of mathematics that was known by this group. From land surveying that had operations in fractions, area, Euclidean algorithms, the use of pi with more accurate estimations than just 3. It did proportional type problems. It could solve areas when you have a missing side, cube roots, square roots. You see concepts of limits being integrated into this well before Leibniz starts to work with them. You see volumes in proportional reasoning, systems of linear equations again, and then also the Pythagorean theorem, right triangles and similar triangles are being used. So concepts again that span different civilizations, even though one may get the credit for it. So here's an example from chapter 9, problem 11. Given a door of which the height is larger than the width by 6 chi and 8 sun, the maximum distance between the vertices is 1 chang. What is the height and width of the door? First thing we'd want to do to a problem like this, we have our door, let's label the parts, and we're going to put them all in the same units. In this case, we're going to make it chi, since that is an equivalent because they use the base 10 system as well, and it gets us the different distances between the sun and the shang. So If we use the width as being w, since that's unknown, we know that the height is the width larger by 6 and 8/10. So that will be our height. And we know it's 8/10 because there are 10 sun and 1 chi, so 8 sun would be 8/10. Now we look at what's the next part. The maximum distance between the vertices is 1 chang. So the maximum distance on this door would be going diagonally across the door. So now look at what shape that we have here. If we look at the two sides on the diagonal, we have a right triangle, something that the ancient Chinese could work with. So now we see that it tells us that's 1 chang. Well, 1 chang is equal to 10 chi. So now we have our right triangle with all three sides. We can use the Pythagorean theorem, something that the ancient Chinese could work with. So we're going to simplify that out. Now, at this point, it's most likely that the ancient Chinese would have used Horner's method to solve this problem. But that is not necessarily known because the answer and how they did it was not given necessarily in this text. So we'll just use the quadratic formula to simplify this quickly. And we'll see that when we do that, we get two solutions of -9 6/10 or 2 and 8/10. Now, because we're dealing with distances and measurements, we cannot have a negative. So we know that the width would have had to be 2 and 8/10. That means that if we substitute that in, that the height would be 9 and 6/10. And based on the solution, we would know that the width is 2 chi and 8 sun and 9 chi and 6 sun for the height. Now, another interesting thing that comes out of the ancient Chinese is the idea of the Lo Shu square. It's said to have date back to about 2000 BCE when there were major floods going through China. And there were sacrifices being given, and it's said that Emperor Yu went to the river and saw this magical turtle that came out of the river with this pattern on its back. And you see that there's a 3x3 array with dots on it that represented numbers. And when you take those 9 numbers, you get the magic square, which has all sorts of unique and interesting properties to it. Because of all these properties and its findings, it led into concepts of numerology and feng shui, and it was seen to have mystical powers. You can actually go online and you can find many sites that talk about the mystical powers of the magic square that continues to this day. But it's spread out of China, and you can see even in places like Turkey and India years later and centuries later, where they would use the magic square to help protect. Women would embroider it on the warriors, hoping that that would help them win the war and come home safely. And it's still today, people look at it as a way to improve their life. Now, the magic square has some key concepts to it. First, it's an n by n square with the rows, columns, and diagonals all add to the same number, and it uses the same numbers consecutively from 1 to n squared. The important piece is that magic constant, which has to be the sum of the row, the diagonal, or the column. And we find that by taking the n, multiplying it by the quantity n squared plus 1, and then dividing by 2. Then we know what every row, column, and diagonal has to add to, and that helps us build each of our magic squares. So if we think about a 3x3 magic square, we know that since it's 3 for the width and 3 for the height, the n value is 3. So 3 times 3 squared plus 1 over 2 will give us 3 times 10 over 2, which is then 15. So we know that each row, column, and diagonal should add to 15. And if here we have a magic square put together, we can see the rows add up to 15, the columns add up to 15, and the two diagonals also add up to 15. Now, we see that the magic squares are pervasive through time. Again, here in 1514, Albert Dürer constructed this image that has his representation of melancholy. And if you look in the back right corner here, we have a 4x4 magic square, which was said to help show cheerful exercise in the heart of all this melancholy that's around. Now, some cool facts about this specific 4x4 is, one, we know that a 4x4 has a magic constant of 34. But this one specifically has two cool things. One, down here, 15 and 14 were put side by side to create the year that he created this printing. Additionally, it's a gnomon square where the 2x2 quadrants, each of those 4 numbers also add up to 34. So it's even a more specific type of 4x4 quadrant. Now, there's a recognition that the even numbered magic squares have some unique properties about how they can be constructed and things that can happen. And so this has continued to lead to different ways people have looked at them. For example, we can look at a 4x4, which is a doubly even magic square, and we get some unique properties that can be helpful in how we can solve them and actually create them. So first thing, we draw our boxes for the array, so it's a 4x4. We next are going to put an X through each 4x4. So if it's an 8x8, we're going to put 4 X's, one in the top left, top right, bottom left, and bottom right. So there'd be 4 X's on an 8x8. So here's our X. Now we're going to go and put in the numbers going left to right, starting with 1, and we only put it where there is not part of that X. But we start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and not 16. Now we're going to go back in reverse order to fill in wherever there is an X, starting at our highest number, which is 16 in this case. So 16, skip, 13, 12, 11, 10, skip, 9, 8, 7, 6, 5, 4, 3, 2, 1. And it's just counting, and we can fill in our even square. And here you can see where these are backwards, we could change those rows and we could get it to where it's the 15, 14 like it was on the last one. Now, magic squares continued to pervade through history, which is kind of interesting what it creates. Euler was known to have invented a modified version that he called the Latin square, where each number had to appear exactly once in each row and column, and it's the origins of what we think of the game Sudoku now. Benjamin Franklin was known to doodle magic squares and even constructed an 8x8 where the bent diagonal, so if you think about a large X going across the whole picture, it would be the 4 down and then the 4 back would create the magic constant as well. And we see it used in other aspects even nowadays, where we can use it to help us build rosters and brackets for tournaments, home layouts with feng shui, and even games like Rubik's Cube have aspects of them that relate back to this magic square, which started with the ancient Chinese.